Hello everyone, welcome to the book and notes. This video is part 5 of Chemistry Class 11 Chapter 3, the periodic classification of element, and here the topic is periodic trends in the properties of the elements. Here, within a period, the chemical reactivity tend to be high in group 1 metal and lower in the element towards the middle of the table, and it increases to maximum in the group 17 non-metal. And likewise, within a group of representative metal, say alkali metal, the reactivity increases on moving down the group, whereas within the group of non-metal, such as halogen, the reactivity decreases down the group. Now, trends in the physical properties are atomic radius. Atomic radius, or the radius of atom, it may be defined as the distance between the atomic nucleus and the outermost shell containing electrons of the atom. And the atomic radius are of three types. Number one is covalent radius, number two is metallic radius, and the number three is van der Waals radius. Here, let us see covalent radius. Covalent radius is the half of the internuclear distance between the two covalently bonded atoms in a homodiatomic molecule. Some of the examples of covalent radius are chlorine molecule, H2 molecule. Here you can see the structure. Now let us come to metallic radius. Metallic radius is defined as internuclear distance between the two closest metal atoms in the metallic crystal, and the structure of the metallic radius is given here, and also the formula of metallic radius can also be said that R metallic, that is metallic radius, is equals to d upon 2, where d is the total distance between the centers of the two atoms. Now let us come to van der Waals radius. Van der Waals radius is the half of the distance between the two identical non-bonded isolated atoms. Now the example of van der Waals radius is given here, and the formula of van der Waals radius, that is RV, is DAA upon 2. Here DAA is the distance between the two different molecules. Okay, now some of the comparison are given here. Here the van der Waals radius is the largest among metallic radius and the covalent radius, and among forces the covalent force is greater than metallic force, and metallic force is greater than van der Waals force. So the smallest force here is van der Waals force. Now the variation of atomic radius in the periodic table. Let us study the variation of atomic radius along the period. The atomic size generally decreases from left to right along a period because within a period the electron is added to the same valence shell, due to which the effective nuclear charge increases, and hence the outer electron is held by the nucleus is more tightly, which result in the decreased radius. Now variation along a group. The atomic radius generally increases on moving down the group because the electrons are added in the successive shell. So the principal quantum number increases, thus the electron in the inner shell shield the electron of principal energy level, due to which the distance between the valence electron and the nucleus increases, and the hence atomic radius increases. Now let us come to the second trend, that is ionic radius. Ionic radius is the effective distance from the center of the nucleus of an ion up to which it has influence in the ionic bond. It can be estimated by measuring the distance between the cation and anion in ionic crystal by X-ray method. It can also be said that internuclear distance is equal to radii of cation plus radii of anion, and the nuclear charge is inversely proportional to the ionic radius of the isoelectronic species. Now let us come to isoelectronic species. What are isoelectronic species? Atoms, molecules or ion which contain the same number of electrons are called isoelectronic species. Some of the examples of isoelectronic species of the same category are O2 minus, F minus, Na positive, Mg2 positive. The radius of the isoelectronic species would be different in their different nuclear charges. The cation with greater positive charge will have smaller radius, and the anion with greater negative charge will have larger radius. Now let us come to the third trend, that is ionization enthalpy. Ionization enthalpy is the minimum amount of energy required to remove an electron from an isolated gaseous atom in its ground state. Now let us come to successive ionization enthalpy. So in successive ionization enthalpy, the first ionization enthalpy is the energy required to remove the most loosely bound electron from isolated gaseous atom. And the second or third or successive ionization enthalpy is the energy required to remove the second electron, third electron, or the successive loosely bound electron from the isolated gaseous atom. There is a question, why ionization enthalpy are always positive? And the answer is, the removal of electron is endothermic process and energy is always required to remove electron from the atom. Hence ionization enthalpy are always positive. Now there is another question, that the second ionization enthalpy is higher than the first ionization energy. In the same way, the third ionization is higher than the second one. Why? And the answer is, it is difficult to remove electron from positively charged ion than from neutral atom. Now let us come to the factor affecting ionization enthalpy. And the factors are screening effect, nuclear charge, penetration effect of electron, and the electronic configuration. Now let us come to variation of ionization enthalpy in the periodic table, and the first variation is along period. On moving from left to right, across a period, the ionization enthalpy increases because of the successive addition of one electron, which results in increased nuclear charge. But since the electrons are added to the orbits of the same principal quantum level, the shielding effect remains the same, and it is not enough to compensate for the increased nuclear charge. The increased nuclear charge overweights the shielding effect across a period. As a result, the outermost electrons are held more and more firmly. In a period, the ionization enthalpy is maximum for noble gases and lowest for alkali metal in a period. Now, the exceptions are, in second period, the ionization potential of beryllium is greater than that of boron, and in the third period, the ionization potential of magnesium is greater than that of aluminium. This is due to high stability of fully filled orbitals. Now, let us come to variation along a group. On moving down the group, the ionization enthalpy decreases because the nuclear charge increases due to the addition of electron. But since the electrons are added to new energy level, the distance between the nucleus and the valence electron increases, and shielding effect on the valence electron increases, due to which increase in number of inner electron. Thank you for watching the video, and do not forget to watch the last part of this video, and there is a PDF link in the description box.